I decided to call this Introduction to Solidification, similar to what happened in the morning, where we were introducing the fundamentals of solidification. This is not intended to be an exhaustive description. It's more of a first touch for those who are unfamiliar with solidification modeling. The same way that for those who are unfamiliar with the fundamentals of solidification in the morning, it was more of an introduction of the basics. And today is the same objective with this, just give you a very general idea of how modeling is used for solidification, and in particular for modeling of casting solidification. And just as in the morning we were discussing, there are multi-scale challenges. Of course, in order to do research on solidification and casting, but also to model solidification and casting. And if we look at it, continuous casting models should be capable of addressing this macro and micro scale, plus the complex physical phenomena happen during this whole chain. And that what we see that we can define as microscale is whatever is happening between 10 to the minus 9, 10 to the minus 6, all the way to 10 to the minus 3. So basically from nanoscale all the way to micro scale or millimeter scale. Then we have what is happening at mesoscale, which is already taking part of the connection with the micro and going all the way to the order of meter in scale. And largely, we address the scale of the casting machine with models such as CFD and FEM. So you can see here that there is no model that really covers the whole range, or not at least in a practical manner that we can solve all the scales at once. So very often we end up focusing in specific models for microscales or a specific model for mesoscale. And now a very rich ground for research is the interconnection between these models, like how you connect CFD or FEM with mesoscale modeling, how you connect mesoscale modeling with the further microscale, and so on. And in fact, I think this is the subject of a research, part of the research going on in Shellcrack. So I think probably Niels and Shailesh will address that later on. Regardless of this, thermodynamic happen everywhere. So we need thermodynamics happening over the whole range. So it's very important to see that there are specific ranges for each model to operate. In the same way that there are ranges for these models to operate, we see that not all models can address all the phenomena. So, and this is due to the multiphysics nature of the problem in casting. So to joke about Lord of the Rings, so there is no one model to rule them all. And the issue with that is that we tend to think that the tool that we use, especially, let's imagine we are a specialist on CFD. So we tend to think that we can solve everything from that approach. And that's mostly not the case. We need a combination of tools, and very often we need specific tools for the tasks. Such examples could be, for example, the meshless methods, which are very appropriate to deal with granular flows, bubbles, and inclusions. Granular flows can easily be found in casting, for example, in terms of how the casting powder moves. The big differences we have in performance between casting powder which comes in powder phase or in granules. So, and definitely non-Newtonian behavior, and which is very hard to model with other methods than the discrete element method or meshless methods. For multi-phase flows, steel, slag, gas, heat transfer, very often solidification at macro scale and electromagnetics, CFD is the preferred method of choice. Whereas for material properties characterizing the phases that we have in the system, whether the reaction, precipitates, or inclusion formation, and so on, we certainly need to address thermodynamic modeling. Finally, the subject of today, and we have gone through, I put the tick marks because we have gone through in the previous sessions with our students and in the past in the previous Seidonor seminar in Spain. through CFD and thermodynamic models. And now we will try to address very shortly the finite element methods and the micro and mesoscale models. Uh, Finite element is typically used to solve what is the status of stress and strain in the strand. Of course, this will lead us to cracking and eventually to understand better what's the end use of the product, like rolling and forging to produce sheet or plate. In terms of microscale, then we focus very much on the solidification evolution, the segregation, and of course the properties that we will achieve depending on the microstructures that we discussed this morning. So the modeling approaches can be various, but I try to put all these confirming in this triangle of influences. And we see on the left side that we can address with CFD things like modeling the stopper and the SEN, the argon injection, flow modeling at very accurate behavior of the turbulence. And this pretty much will describe the flow dynamics in the system. And talking to our students in the morning, I was telling them that the definition of casting is extracting heat from a melt to form a solid. And here we see the three components: the melt, represented by the flow dynamics on the left side, the heat extraction that you have on the right side. And very often we need to understand very clearly what kind of properties and phases we observe. And we do this often with CalPAT and finite differences, and finite element as well is used. And finally, the solid formation, which is very strongly dependent on the coupling with the cooling rate that we discussed this morning. Then we end up with this combination of fluid dynamics, heat transfer, and solid behavior that, in the best case scenario for our castings and for our processes, leads us to a good product. But when any of these three components is failing, or is not doing, we are not doing appropriately in any of these three, we lead to the formation of defects. And hopefully we have the chance to have another final session where we will explore these defects in more detail. So now, without further ado, I have also a bit of quick of a modeling timeline. And this I would strongly recommend. I didn't put here the paper that we just recently published with our group on Metacast with Michele De Santis as leading author. So I would recommend, if you, Michele, have the chance to please post the link to the Open Europe publication, will be fantastic, so they could look at the results from Metacast and they can have a read on this background on modeling. And also we did the mapping of expertise of modeling in Europe in casting. But to summarize quickly, we saw already from the 70s and 80s, with the advent of personal computers, a first generation of models. And these are the classic models that we have seen from Bremacom. We have seen also the classic model from Pritchard, very often based on thermocouple data, where we do a backfitting of the heat fluxes in the system, and then we are able to do a qualified guess on what's the shell growth and what would be the thicknesses as we progress in the casting machine. So these were in the 70s the beginning of the modeling of casting and solidification. Then further on in the 90s, with the addition of the CFD approach and the different approaches for solidification, we could see already publications by Professor Thomas, Julian Sekeli, and the other teams, von Wohler and so on, to model solidification in the 80s. Further on, with faster computers in the 90s, we can see a huge progress in multi-phase applications. For example, now we can see the effect of bubbles and inclusions on the simulations, combined with the calculations of solidification and flow in the past decade. And it's amazing. We just have Seppo joining here because we're mentioning here you, Seppo, that you already were doing this research with alongside Brian Thomas and Andreas Ludwig and yourself, doing the coupling of multi-phase phenomena with solidification. So that's already happening in the 90s. And by the 2000s, we have a variety now of commercial and in-house codes capable of doing modeling of continuous casting. We have amongst them Procast, COMSOL, TempSimo, Con1D, etc., Con2D. But what is the trend now? Where are we going now? And the recent trend is that the development of thermomechanical models are coupled now with flow dynamics. So what I was mentioning about this CFD and FEM being separated is coming to be not true anymore. So we are now having monolithic solvers that are capable to address flow dynamics and solidification and stress strain and due to solidification in a complete way, in a more holistic way. Amongst these, I can mention perhaps Physica in the UK. I can mention, of course, Tercas from Transvalor in France, and there are plenty of initiatives that are trying to go into that direction. So this gives you a panorama of what are the modeling tools available nowadays. And without further ado, I will try to map a bit of what is the approach in microstructure modeling. In this case, we discussed this morning about the fundamentals of solidification. We talked about nucleation and growth, and we are trying with the microstructure modeling that we do to reproduce the formation of grains, dendrites, and the different phases we encounter. Often also we want to understand segregation and the formation of porosity. So at present we have, again, I'm not trying to be exhaustive in this review, but we can group it into three: the deterministic methods, the stochastic methods, and I will add on the mesoscopic methods, which are working in a bit higher scale. As a quick example, let's remind us the ingot that we've been looking into the different presentations and the slides today. So we are trying to understand what is the, let me bring my pointer. We are trying to understand what's the evolution in terms of transport of heat and solute as we proceed in solidification, in order to be able to understand where we have, for example, columnar growth, where we have this transition to equiax, what's the fraction of equiax we have, and what's the influence in many cases of these thermosolutal convection currents that we saw in the videos before the launch time. So that's, let's say, setting the scene on what we are trying to achieve. And in case of deterministic modeling, well, it's first of all based on classical solidification kinetics and crystal growth characteristics. So in this case, the functions such as crystal nucleation, density, and growth rate in the melt are derived, and they can describe the change on density of nucleation and dendritic growth, but they won't be as specific as to where this is happening, but it would be some sort of average approach. And in this sense, we have three types, which are the most common, and they are the mixture theory, the volume averaging, and the ensemble averaging. I will start first by mentioning what's the fundamental for this approach, which is the representative volume element. So let's consider the volume element, which is located in the Mushi zone. For those who haven't attended the session in the morning, we had a quite intense session where we look at a lot of videos where we were trying to understand what is the behavior of the solidification front, how we have a Mushi zone and interdendritic liquid in between, and what the representative volume element is trying to portray is as some sort of average representation. If we look at it, in this case from the top, as a cross-section, we are trying to represent what is happening in detail in all this picture by taking just a roughly percentage of how much of this area is covered by solid, how much is covered by liquid, and then make it this as a representation of the solid fraction. If we translate to the 3D, then we will have here representation of the volume. If you can do it in 2D as well, and in general, this RBE will be defined by the size of the mesh that you are operating with. But I will come to that in a second. So one way to draw parallels between what happens in the real life, and you remember this diagram in the morning where we had the solidification range between T liquidus and T solidus. We have this whole set of temperatures in between: zero strain temperature, liquid impenetrable temperature, and the zero ductility temperature. So this is real life, what you see here. In a deterministic model, you don't see that level of detail because you are only applying the equations that describe the general growth, not the specific growth in certain positions. A good example of this is the lever rule type of model that we use in Fluent to describe the solidification based on the isotherms between T liquidus and T solidus. We can also define in Fluent, for example, the CDT, which will help us to define what's the pulling velocity. So in this case, we will say to Fluent, whatever comes to this point, it will be part of the movement of the shell and it will be pushed out. And that would be obviously the casting speed. But everything in between, we have only the information as a gradient. So this is the classic way to describe a deterministic model. So what are the limitations of it? Here I have a very interesting publication by the group of Combo. So it is possible to use deterministic models to try to address things like liquid pool depth, the shape of the mushy zone. Of course, it's harder to take into account grain motion, and that's why I take this publication as an example, because it's an effort to portray this grain motion and the transport of grains which are collecting them, and as you saw in the previous videos that we had, how the actual transport of grains can also act as nucleation sites when you break off a dendrite arm, for example, and becomes now a nuclei for a new grain and so on. So portraying this is actually very challenging in deterministic model. So what are the pros and cons? Well, the pros is that they are fast because we are not resolving the whole microstructure, but we get a really good view of the overall performance. They are easier, well, I wouldn't say easy, maybe I should correct here. They're easier to code than stochastic models, and they require relatively low computational time. So as long as we know the heat transfer profile in our casting, it is possible to make a prediction of a deterministic model. And it is very ubiquitous, so as you could see, we use it in Fluent very often in our digital twin to predict the solidification. And from there, you can go child type, you can go level rule, and you can go everything in between. So they are possible to be modified in a more or less rapid way. What are the cons? That, of course, is not possible to describe random phenomena due to solidification. We see that solidification is very random. We were just chatting with our students at the end of the session, and one of them was saying, yeah, but I never thought that there were so many considerations when we have, for example, snowflakes. And we ended up discussing why snowflakes are different from each other. And it's because the events that every nuclei that later became a snowflake are different. And this randomness we miss in these deterministic models. We will get a distribution, but very often we will end up predicting the same shape. For example, if we are modeling a snowflake, we will end up predicting the same shape. Whereas the reality is that we will always have some random nucleation events. The same happens with the crystal orientation. It will be random. The columnar to aqueous transition will be difficult to predict. Now, there's ways to do it also in deterministic, but in general, it will be more difficult. What we saw, for example, in the videos this morning about competitive elimination of dendrites and how the grains, the solidification fronts collide and form grains in very peculiar ways that, for example, are as a function of a flow when we are having in the slab, in the corners, or in the specific areas of a component, this level of detail we miss. So we don't get this information on grain evolution. We have an average grain size. We do have, because we have the heat transfer profile, we can calculate what's the average grain size distribution. However, we don't have these effects of competitive elimination of dendrites. And the same goes for fusing and bifurcation of dendrite arms, breaking off our arms to form new nucleation sites. All these effects are lost. And that's the reason why we approach the stochastic models. So the stochastic methods divide the calculation element into microelements in some sort of grid, and then the grain nucleation and growth on each node are calculated according to probability models. So often these methods treat the grid element as a cell, and the state values of the cell include physical parameters such as temperature, solubility, solid fraction, growth, and so on. So for those who are familiar probably with the 80s and 90s and played video games, you probably remember Pac-Man. And it's pretty much like Pac-Man if you want to think about it. How you solve equations and go from one place to another. And I have a couple of examples on this. So basically, at each step that we take, every movement, the state values of each cell and the transition of the interface are realized by solving the control equations, and then they are captured in an algorithm. We have three general types. I would say, again, it's not exhaustive review: Monte Carlo methods, cellular automaton, and phase field. If I'm correct, Niels and Salish will talk a bit about phase field with the work of we are doing in Micrest in Shellcrack. And I will just, to give you a good example of how it works, I will talk about cellular automaton. So cellular automaton is a model that simulates the process of liquid turning into solid, that the solidification part, but is based into a grid of discrete cells. So each state cell is determined by simple rules. So you remember I was telling you about Pac-Man, or maybe we can talk about Chinese checkers as well. So basically, we have a grid where they jump to the next positioning based on a very simple set of rules, which is what actually defines the solidification rules based on its neighbors, and they mimics processes like nucleation and crystal growth. And this approach is rather efficient because you only need to track the interface as it is being formed. Here you have two approaches on how to start with, and how a matrix on advancement of this solidification front happens. And in fact, these very simple rules create a lot of complexity. So here you have on the right side a dendrite, which has been predicted with a cellular automaton model. And it's pretty much like nature. So I would say simple rules, for example, if we think about a tree in nature, and the rules are rather straightforward. For example, that as long as we have this root of the branch, and the branch grows half a meter, divide into two branches. And every time that it grows 30 centimeters after that branching, divide into two. And we see that these very simple rules in nature very often lead to complexity. And that's exactly the case with a cellular automaton. Very simple rules for moving from one cell to the other can lead to complexity when they interact with the heat transfer profile, but also with their neighbors and with the overall process conditions. I have some cellular automaton videos to show you what I mean with that process, competitive process. Here we have, for example, I hope you're able to see my screen. Please let me know if you don't.
Yes, we have. Yes, we see.
Yes. So in this very competitive process, so we have simple rules. For example, we have here a dendrite growing in the four directions, and we have the primary arms growing, and each arm is growing secondary arms, which is interacting with the rest of the dendrite. And at first, it seems rather simple, but as the solidification proceeds, then we see more and more complexity as the arms interact with each other. If I do the same with the next video, which is this one, give me 1 second, right here, we can see that the same rules, depending on the anisotropy factors that we observed in the previous solidification session in the morning, can lead to extreme complexity depending on how they interact and the patterns that we form at the end. And this is just based on this, you can call it Pac-Man or Chinese checker game of how the solidification moves from one cell to another. So what are the pros, cons of deterministic models? Well, the pros, they can consider complex phenomena in the solidification process. So everything that we miss from the sorry, and here should be stochastic. Just correct it as fast as I can. So random nucleation distributions, random crystal orientation. We can find the CET, the competitive elimination of dendrites, and the fusion and bifurcation of arms. So all these phenomena we can capture with a stochastic model. Sorry, it was not deterministic, stochastic. What are the cons? Well, they are computationally expensive, of course, because as you can imagine, producing this kind of cellular automaton per dendrite or per nuclei in the whole domain, especially when you're looking into bigger casting sections, is computationally very expensive. It also requires user inputs for microstructure. So in this case, for example, that we have of this figure, let me go back to the and swap. So in this case, we determine based on previous microstructural observations for these specific alloys, we know what's the anisotropy, we know what are the preferential growth axes for this specific dendrite. So we have to predetermine these in our models. So it's hard to really do from scratch a prediction which is accurate unless we have prior knowledge on the microstructure. So basically, we require user inputs for microstructure. It is, of course, slow because we need to grow the structure from scratch. And very often, it means that we have to limit our calculation domain to the order of millimeters. It means also requires coding experience. The number of available codes for this is limited. However, there are codes that are addressing this. Micros is a good example. I think Salish probably will talk a bit about it later on the shell crack session. Then I will move now into the mesoscopic method. So the mesoscopic, as you saw, they are falling in between the macro scale and the micro, and they are addressed for bridging this gap in terms of calculation from the micro to the macro. And so for this, they are designed to be faster. And the approach is to use typically an envelope that simplifies the dendritic grain into a smooth virtual surface. This envelope links the active dendrite branches, and its growth is calculated from the tip growth velocity of the dendrites, and these are themselves determined by the local liquid supersaturation. It is a multi-scale model, and as I mentioned, is for bridging the gap between micro and macro. For this, I choose an example this excellent publication by Professor Berkerman and Comboa and their collaborators. Here we can see a classic envelope model, which can accurately predict microstructure features like dendrite shapes and grain interaction. So you do get these grain competitive effects. They offer faster simulation times compared to phase field methods, and it's possible to analyze complex phenomena such as hot tearing in welding or microstructure evolution in additive manufacturing. Here I mentioned a bit about the approach. So you can see that instead of why they are faster, because instead of resolving all this complexity of the dendrite as we progress with the growth, we are representing this as an envelope over this, shall we say, area. And this allows us to be faster because we are just calculating the velocity of the tip or the solidification front for a more generalized area. And therefore, you get this kind of profiles for the grains, even if you don't resolve exactly secondary errors. Finally, I don't know how am I doing on time? Yeah, I have a few minutes more.
You're good.
So finite element methods. I decided to include finite element methods because they are very important for casting. But despite all the progress, the actual simulation of cracking and very often combining with solidification during casting has remained elusive from our modeling efforts. And this is why this is due to the multi-physics nature that we described at the beginning of this lecture. And the problem is dependent on the heat transfer, solidification, and stress strain. And of course, with the high temperatures, which limits what kind of possible data we can acquire. I think shell crack in this case is trying to bridge that gap too. So, hello?
Nothing, Paul. Go for it.
Oh, yeah. So cracking modeling. So the process models are typically based on macro scale FEM methods that aim at predicting total strain and stress. I bring as an example this excellent publication from Professor Thomas and Professor Michel Bellet in France, and that address the distortion and hot tearing. So here you can see the classic corner of a billet, and you can see actually the formation of a depression on this side, which is very likely the responsible for this internal crack formation. And here you can see a good example of how FEM is used to predict this location, but we haven't got to the point yet where we can see open cracks in the calculations, although I'm sure we are going into that direction. From our side, at this very moment, I would like to bring up a FEM model example where we are taking the shells in a similar approach as taking these breakout shells, assuming that the shrinkage from cooling is reversible. So it's a very controversial approach, but it helps us to set easier boundary conditions for shell growth and shell resistance. So, and in this case, we take it as a 2D slice, but this 2D slice is basically going upwards or reversible, and then we are moving the mold in according to the actual taper for the wide size or for the narrow size for you who are familiar with casting. So what do we get is a very interesting simulation where we can observe for a given shell, we can observe the evolution of the stresses as they progress. Of course, you need to think about it is in a reverse way, but at the end of the day, what we are trying to understand here is the tapering conditions of the mold against the shell, and whenever we lose contact. So you see here very clearly in some sections how we lose contact with the narrow face and what this generates, which is the separation of the tip from the wall. So this is in terms of strain, and it helps us to understand better, for example, when we have good contact or not, the formation or accumulation of stress as a function of specific shells that we obtain either from etching with the help of our students, for example, which done superb work on etching in samples from big slabs, and they have translated these shells into FEM. Or from our digital twin calculations in Fluent, for example, we are able to extract these shells and put them under this reverse modeling approach. I think I'm spot on, so I have 5 minutes more. I will talk about, just to summarize, on terms of microstructure. So we have seen today, we have 3 scales that we are trying to address solidification and casting. So we have the microstructure scale, the mesoscale models, and the macro scale. In the microstructure, we are trying to have high resolution to predict what are the structures during solidification. It should be coupled with thermocalc and the properties. And very often we focus in small computational domains in the order of microns. They have a high computational cost often. And that's the reason we are trying to couple them with mesoscale models, which are capable of predicting the fluid flow as well as the solidification part, but they have more potential to be applied to industrial scale problems because they have a more moderate computational cost. They lack features, but they are a good compromise compared to the microstructure models. I'm not saying that we should apply only mesoscale. I'm saying is we need a combination of both. And finally, in the previous sessions, and I think also in the Spanish lecture that we had some months ago, we talked about the CFD and the macro scale model. We know that is very applicable to industrial scale, and the computational cost is lower depending on what kind of multi-phase phenomena we are addressing. And it's possible to couple with the slag metal reactions with the thermodynamic databases. It is possible also to add multiphysics like EMS, argon injection, and so on. But we miss a lot of information in terms of microstructure and segregation. So we need to cover pretty much all this scale to address many of the issues in casting. But before pressing any button, and just as a final example of what we are trying to achieve here, is it is necessary first to define the outreach of the modeling. What are the needs? What are the expectations from the analysis? Because modeling requires significant resources in terms of hardware, software, and manpower. And I always use this example of the operations research with this survivorship bias example from the Second World War, where the U.S. was trying to enhance the durability of their planes. They were having losses, and one of the analysis that they decided is to put better armor or more armor in the planes. And the approach was to see where the planes had more bullet holes, and then decide to cover these sections. When they analyzed planes which were coming back with bullet holes, they decided, well, maybe we should put here the armor. And in fact, this is a wrong approach, because in fact, the planes that were able to come back with the holes were in the sections that they could survive because they were not critical. So then you can see that the areas without bullet holes were the planes that were hit on those areas were the ones that didn't come back. So this is an example of how the problem set up can lead to false approximations in terms of the problem that you want to solve. So before going and pressing any button, I would say first you need to think about why is this simulation required? What are the problem boundaries? What are the size and geometrical constraints? And even before that, if it's possible to have an experimental evidence and understanding what is the possible behavior of the problem at a theoretical stage and understanding in a causal manner, it would be very important before you do any simulation at all. And it ends up in many cases here at Sperring, for example, when we are requested to do a modeling project that, well, modeling is not necessarily the answer. Maybe an experiment or maybe a measurement in the plant is the way to go forward. So this is also for you to bear in mind. We don't need to do modeling just for the sake of modeling. Yeah, I hope I'm spot on 15.
Thank you so much, Paul. Maybe we can have one question, and if there are more questions, maybe we'll take it at the end of the session.